Okay, so I'm going to be doing problem number 9. The diagram at the right shows a slightly different form of... you can read the question yourselves. So, first things first, we have to calculate the speed of the particle when it leaves, when it basically enters the magnetic field. So, the only things that we have for that is basically delta V and Q. So we need to get the speed by using the delta V and Q. So we know that delta V, delta V is equal to delta U over Q. That was from chapter 4 or whatever, I believe. And from the mechanics, we know that basically the change in potential is equal to change in kinetic. So that's basically going to be delta K over Q, which is going to be 1/2 mv squared over Q, which is delta V. Now if we solve for V, we're going to get, what are we going to get? Delta V to Q over m root. So that's our speed. We also learned that R is equal to mv over qb. So if we just substitute V, we're going to get m root delta V to Q over m, the whole thing over Q and B. So we just square the whole thing. R2 is equal to m2 over m, and then delta V to Q over Q squared B squared. And then remember that R2 is radius, so it's going to be equal to x2 over 4. Yeah, so now we have this. This is going to cancel out. That's going to cancel out. If we solve for m, we're going to get m is equal to x2 b2 over 8 delta V. Yeah, is that it? I don't know. I think so. Yeah. No, that was not it. There's also a Q here. So that's basically how we do number 9. And also a hint for number 10. How you get that equation is basically by square rooting both sides and then multiplying by root m. So that's going to be root m is equal to root q over 8 delta v, and then if you multiply the whole thing by root m, you're going to get m is equal to x b root q m over 8 delta v, and then you just basically m2 minus m1, you do the same thing, and then delta m, since it's going to be under a square root, it's going to be negligible, so you just can ignore that, and then you're going to get that. So that was the hint for number 10.